You can do a lot more with images than just scaling. You can do anything you want because you have direct access to each pixel. Recall from 2 lessons back how scaling was done with the replication filter. Actually, all scaling is done with filters. It's just that they appear inside and we don't see them. If you want to do something to an image, all you have to do is write a filter and pass the image through it. All you have to do inside the filter is diddle with the pixels as they come through. I have written such a filter. It doesn't do much. It just makes a picture darker by replacing all the colors by 2/3 of their original value. Now, here's what the program looks like. This is the filter. Notice that all pixel level image filters extend from the image filter class. Now this superclass does a lot of work for you in the filter. It actually gets the image internals and passes them through the filtering methods in such a form that you can address each individual pixel. This method, setHints, is inserted here and overrides the one in the superclass. This method is called by the software using the filter to set the pattern of hints about how it's going to go about doing its job. There's a bunch of weird stuff here, and it can be an interesting area of study if you want to dig into the documentation on it. But the only thing you need to do is set the hint that determines the order that you want to receive the pixels. I like mine in top, down, left, right because that's the way I think of them appearing on the screen. If you want them in a different order, go ahead. But when you get tangled up about what's where, don't say I didn't warn you. Once you set your hints the way you want them, you'll need to call the method in the superclass so it can record the hint information. This method, setPixels, is the one that does all the work. As you can see, this method is called with a bunch of arguments that contain the numeric values of all the pixels and the size of the image itself. The stuff passed in can be the whole picture or it can be part of the picture. If the offset value is greater than 0, the stuff passed in is not the beginning of the picture. But this only happens if the picture is big enough to be sent through here in parts. It's usually the whole thing coming through, so the offset value is usually 0, but don't count on it. Now the pixels themselves come in here as an array, but the actual content of the array is dependent on the color model, which is also passed in. By the way, if the scan size is less than the product of the height and the width, you haven't been sent the whole picture. This is the declaration of an integer array reference. This reference will hold the address of the array of colors for each pixel. Now, this array is where you're going to store the new pixels produced by this method. And everything is done in a loop. The outer loop is set up with px to count the pixels in the width, and the inner loop is set up with py to count the number of lines of pixels. With px and py addressing one pixel in an image, this line of code calculates the subscript of that pixel in the incoming array. Notice that the offset value is added. In case the incoming array doesn't start at the very beginning, the offset value would be non-zero. Now I know this is a little screwy, but don't yell at me, I'm just the messenger. Now right here we have found the pixel we want to mess with. Each pixel is composed of the intensities of the 3 primary colors. Different color models pack the primary colors in different ways, so it's necessary to call the getComponents method of the current color model and have it break out the 3 color values for you. These 3 values are stored in the CO array, and now we've got something that we can mess with.